Right now, while you are watching this video, you are spinning. You can't feel it, but you are. The Earth is rotating at 1,037 miles per hour at the equator, faster than any commercial airline has ever flown. And you don't feel any of it because everything around you, the air, the trees, the buildings, your house, your body, all of it is rotating with you. The motion only becomes visible when you compare yourself to something not on the planet, like the stars. And it doesn't stop there. The Earth is also orbiting the Sun at 67,000 miles per hour. The Sun is dragging the entire solar system around the center of the Milky Way at roughly 490,000 miles per hour. And the Milky Way itself is hurtling through the universe at over 1.3 million miles per hour. You are spinning, orbiting, rotating, and accelerating across multiple frames of reference at the same time. And so is everything else. Atoms spin, planets spin, stars spin, galaxies spin, black holes spin so fast that the space-time around them gets dragged along for the ride. In the entire observable universe, nothing actually stands still. Why? Why is rotation the universe's most fundamental form of motion? Where did all of this spinning come from? And what would happen if it all stopped? The answers will take us from the first fraction of a second after the Big Bang through the death of stars, all the way to the inside of a single atom. By the end, you'll see the cosmos as one continuous dance. To understand why the universe spins, you have to go back to its very first moments. About 13.8 billion years ago, the universe began as a hot, dense state that expanded outward in all directions. This is the Big Bang. And here is the first thing that surprises most people. The Big Bang itself was not rotating. Cosmologists have measured the universe at the largest scales. The total angular momentum of everything added up is essentially zero. There is no overall spin to the cosmos. So if the universe as a whole is not spinning, where does all the rotation come from? The answer is in how the early universe broke up into pieces. Matter spread out into vast clouds of hydrogen and helium gas. These clouds were not perfectly uniform. There were tiny fluctuations in density, regions just a fraction of a percent denser than their surroundings. They began to collapse under their own gravity. Inside each collapsing cloud, gas particles were already moving in random directions. By pure statistics, those motions never canceled out perfectly. Each cloud ended up with a tiny net rotation. Tiny, but not zero. And once a cloud has any rotation at all, the laws of physics take over. There is one law of physics that explains almost every rotation we see in the universe. It's called the conservation of angular momentum. And the easiest way to understand it is to watch a figure skater. A figure skater on ice begins her spin with her arms stretched wide. She turns slowly, then she pulls her arms in toward her body. She speeds up dramatically. Without pushing off the ice, without using extra muscle force, just by changing the shape of her body, she goes from a slow spin to a blur in less than 2 seconds. Why? Because the angular momentum she has, the total amount of rotation in her body, has to be conserved. It cannot disappear. Angular momentum depends on two things: how fast you are spinning and how spread out your mass is from the center of rotation. When the skater pulls her arms in, she shrinks the distance between her mass and her center. To keep the total the same, her spin rate has to increase. Mass closer to center plus same angular momentum equals faster rotation. This is not a metaphor. This is the actual mathematics of the universe, and it applies to every single thing that rotates at every scale we have ever observed. A cloud of gas 1,000 light years across with the slightest hint of initial rotation collapses under its own gravity. The cloud shrinks, angular momentum is conserved. So the cloud spins faster and faster and faster. By the time it has collapsed enough to ignite a star at its center, the rotation has gone from imperceptible to dramatic. This is why every star in the universe spins. This is why every planet spins. This is why we have day and night. It all started with a tiny cosmic rotation that gravity squeezed into something much bigger. Now let's see what conservation of angular momentum actually does in a real cosmic event. A cloud of gas with a tiny initial rotation begins to collapse under gravity. As it shrinks, the rotation accelerates and the cloud changes shape. It does not collapse into a perfect sphere. It cannot. The rotation makes that physically impossible. Instead, the cloud flattens into a disk. Think about a pizza chef tossing dough in the air. The dough goes up as a ball. As it spins, it flattens out into a flat disk. Centrifugal force pushes mass outward at the equator, while gravity pulls everything inward toward the center. The result is always a disk. Stars are born inside these disks, planets too. At the very center of the spinning disk, the gas piles up into a hot, dense ball. When the temperature reaches about 10 million degrees, hydrogen atoms start fusing into helium and a new star ignites. Around it, in the rest of the disk, smaller chunks and dust of rock collide and stick together over millions of years. Eventually, those chunks become planets. And here is the elegant part. Because they all form from the same rotating disk, the planets all orbit the central star in roughly the same plane, and they all rotate in roughly the same direction. Look at our solar system. Every planet orbits the sun on roughly the same flat plane. Every planet except for two rotates in the same direction the sun rotates. Mercury, Earth, Mars, Jupiter, Saturn, Neptune, they all spin counterclockwise when viewed from above the sun's north pole. Venus rotates backward, Uranus rotates on its side. Those two are the exceptions. The leading explanation for both is collisions, massive impacts in the early solar system that knocked them off their original spin. Now let's zoom out and then zoom in to see how rotation works across every scale of the universe. Start small as it gets. Inside every atom, electrons move around the nucleus. They also have a property physicists call spin. It's not exactly the same as a planet rotating on its axis because at quantum scales, the rules are stranger and more counterintuitive than everyday experience. But every electron, every proton, every neutron in the universe has angular momentum. This means the smallest building blocks of matter are themselves spinning. The atoms in your body, all of them, are made of particles with angular momentum. The carbon in your bones, the iron in your blood, every single atom is, at the quantum level, in motion. Zoom out a little, up to the scale of stars. Our sun rotates once every 25 days at the equator and once every 35 days at the poles. The sun is not a solid object, so different latitudes spin at different rates. This is called differential rotation. Zoom out further to the entire Milky Way. Our galaxy is a flattened disk of stars, gas, and dust about 100,000 light-years across. It rotates slowly, but at galactic scales, slow translates into incomprehensible speed. Our solar system, near the outer edge of the disk, moves around the galactic center at 490,000 miles per hour. It takes us about 225 million years to complete a single orbit. The last time our solar system was in this exact position in the Milky Way, the dinosaurs had not yet evolved. The next time it returns to this position, our species will almost certainly be long gone. Zoom out one more time to galaxy clusters, the largest gravitationally bound structures in the universe. Even these rotate, slowly, almost imperceptibly, but they rotate. From the smallest electron in a hydrogen atom to clusters containing thousands of galaxies, the universe is structured around rotation, every single scale. Now, let's look at the extremes. Conservation of angular momentum has produced some of the most extraordinary objects ever discovered. When a massive star runs out of fuel and collapses, its core can shrink to an object only a few miles across, while keeping all the angular momentum the original star had. The result is a neutron star. And because the core has shrunk so dramatically, the spin rate becomes extreme. Imagine a figure skater with the mass of an entire star, who has just collapsed her arms from the size of a galaxy to the size of a city. The math is absurd. The result is a real object. The fastest known neutron star, a pulsar called PSR J1748-2446 AD, rotates 716 times every second. Read that again, 716 times per second. An object with the mass of our sun packed into a sphere about the size of a city, spinning so fast that its surface moves at a significant fraction of the speed of light. A blender cannot match this. A jet engine cannot match this. The fastest industrial centrifuges humans have ever built cannot match this. Neutron stars are not even the most extreme. Black holes are. When a black hole is formed from a collapsing star, it can inherit a tremendous amount of angular momentum. The spin warps the space-time around the black hole so severely that nothing inside a region called the ergosphere can stand still, even moving at the speed of light. Anything that enters that region is forced to rotate with the black hole. The fastest known black hole is GRS 1915+105 in our own galaxy. It rotates approximately 1,150 times per second, close to the theoretical maximum allowed by Einstein's equations. Spin a black hole any faster than that and the math breaks down. Conservation of angular momentum, the same law that makes a figure skater speed up, drives the most extreme rotation rates in the known universe. Now for the question that gives this video its philosophical edge. What would happen if the rotation stopped? Not just on Earth, everywhere. Start with our planet. If Earth suddenly stopped rotating, the consequences would be catastrophic. The atmosphere would not stop with the planet. It would keep moving at 1,037 miles per hour relative to the now stationary surface. Wind speeds would tear apart cities. The oceans would rush toward the poles, leaving a single supercontinent at the equator. The day-night cycle that drives weather, climate, and biology would collapse. Now, imagine the sun stopping. Without rotation, the sun's magnetic field would weaken dramatically. The cycle of solar storms that protects the inner solar system from cosmic radiation would change in ways we don't fully understand. Without rotation, planets would still orbit because orbital motion is different from spin. But without their own spin, they would have no day-night cycle. One phase would be cooked to thousands of degrees. The other would freeze toward absolute zero. Almost nothing could survive on the surface. Now, zoom out further. Imagine the Milky Way stopping its rotation. Galaxies are held together by a balance between gravity, which pulls everything inward, and angular momentum, which throws everything outward. Without rotation, there is no balance. Every star in the galaxy would begin falling toward the central supermassive black hole. Within a few 100 million years, the entire galaxy would collapse into a single supermassive black hole at its center. The Milky Way as we know it would cease to exist. But here is the thing. None of this can happen. Because conservation of angular momentum is one of the most fundamental laws in all of physics, it's not just a useful approximation. It is locked into the geometry of space and time itself. As long as the universe exists in anything like its current form, things will keep spinning. Atoms will spin, planets will spin, stars will spin, galaxies will spin, forever. The next time you watch a figure skater on television pulling her arms in and spinning faster, remember what you're actually looking at. You're looking at the same physical law that makes a galaxy form. The same law that drives the rotation of a black hole at the center of our Milky Way. The same law that gives every electron in your body its angular momentum. The same law that billions of years ago took a microscopic fluctuation in a cloud of cosmic gas and turned it into the rotating disk that became our solar system, our planet, and ultimately you. The universe is not still. It has never been still. From the smallest atom to the largest cluster of galaxies, everything is moving, orbiting, rotating, spiraling. It is a single, continuous dance governed by one law and one origin, and you are part of it. Right now, as you watch this, you are spinning, orbiting a star, riding a galaxy, carried along by a universe that has not stopped moving since the first fraction of a second after the Big Bang. And it never will. If the cosmic dance fascinates you, there is one planet that breaks the rules. Venus rotates backward in the opposite direction of every other planet in the solar system. What invisible event in the early solar system flipped it around? Watch Why Does Venus Spin Differently to find out what really happened.